Alright, we're going to look at something called periodic trends. And these are just trends that happen on a periodic table. Trend being something that generally will happen as you move along the periodic table, whether you move up to down or left to right. Doesn't mean it's going to happen every single time. There might be exceptions to the rule, of course, but these are generally things that you can predict based on where an element is on the periodic table. So to define it, a periodic trend is a characteristic of an element based on its position on the periodic table. A characteristic of an element based on its position on the periodic table. Okay. First one we're going to look at is atomic radius. An atomic radius is just what it sounds like. A radius is the distance from basically the center of a circle to the outer part of a circle. It's the same thing here. It's going to be the distance from the center, which we call the nucleus, to the outer part of the circle, which we call valence electrons. Valence electrons are the electrons in the outermost ring. So if you're doing electron configuration, it goes up to like 4s2. The 4 is your biggest number, so that's going to be your outer ring. So whichever one's your biggest number, 1 through 7, your biggest quantum number, will be your outermost electrons. So it's a distance from the nucleus to the valence electrons. Remember, valence would be your outermost electrons. They're the ones in the outside ring. As we go down a family, we have hydrogen. We're going to call that the nucleus. Hydrogen is a 1s1. 1 is a sphere, 1 electron. Lithium is 1s2, 2s1. So the first energy level is a sphere with 2 electrons. The second energy level is also a sphere with 1 electron. Now you'll notice, what about the radius? As you go down, it increases. And this is because we have more energy levels, so we have more rings around your nucleus. So you could put more energy levels, just so you know why when you go back to study. Now going across isn't quite as obvious to see, but as we go across, it's actually going to decrease. And here's the reason why. You'll notice on the periodic table, if we start, let's say, with sodium, it has 1, 2, 3 rings, right? Because you can go all the way to 7. So it has 3 rings. Now if we go across, let's say to chlorine, okay, it still has 3 rings. Okay, it's still in the same row. It still has 3 rings. But sodium has 11 protons pulling on those 3 rings. Chlorine has 17 protons pulling on those 3 rings. So the chlorine is going to be able to pull it in a little bit tighter because that nuclear force of the nucleus, is able to pull in those electrons a little bit closer. So as we go across, it's going to decrease because nucleus protons increase while energy levels remains constant. So that's atomic radius. As you go down, it gets bigger. As you go across, it gets smaller. Now, ionic radius is a little different. This one you can tell at the periodic table, but sometimes they might compare like just the element with the ion. And when you have those two, it's hard to compare in the periodic table because they're the same thing. Li and Li plus 1, they're both lithium. So we're going to look at ionic radius, and that's the distance from the nucleus to the valence electrons of an ion. Distance from the nucleus. Oh, it's going to combine this there. Let's try that again. From the nucleus to the valence electron of an ion. So we're going to look at a cation first. Remember a cation? A cat, cute, furry, positive. Cation is a positively charged particle for ion. I want to re-say the word ion again. So a cation is something that loses electrons. An anion is the opposite. We'll do that in a second. It is like an onion. When you cut an onion, it makes you cry. It's negative. A negatively charged ion. So it's going to gain electrons because electrons are negative. So if we're looking at lithium, say that's the nucleus. I'm drawing it as a dot because we really don't care what's going on in the nucleus right now. We're looking at the electrons. And I'm drawing the Bohr model only because on the board, it's a lot easier to draw. First energy level, 2 electrons. Second energy level, 1 electron. It's 1s2, 2s1. Now if I go to the lithium plus 1 ion, it means it's going to lose 1 electron. It's got this one outside here in the outside ring. That's the one it's going to lose. So it's going to go from that kind of a shape. It's still going to have the 1s, but instead of being 1s2, 2s1, it's just going to be 1s2. So it's 1s2, 2s1. It loses an electron, becomes like the noble gas helium. It's just 1s2. It is more stable in this case as far as whether it's going to lose more or less electrons. It's also ready to bond. So you have less electrons, it's more ready to bond. It's more stable because it is like a noble gas, which is inert. But look at the radius. It definitely decreases. So between the atom itself and the cation has a smaller radius than the atom itself. Now if we look at the anion, like fluorine. Fluorine is 1s2, 2s2, 2p6, or 2p5, sorry. 1s2, 2s2, 2p5. I put all my valence electrons on the same ring, just so I don't have to do those p shapes. So this is a Bohr model, 1s2, 2s2, 2p5. So the first energy level, I have a sphere, I have 2 electrons. Second energy level, I put all my s's and p's together, that's why there's 7 dashes there, or 7 electrons. Now I'm going to go over here, I'm going to have a negative 1. Now remember, with a negative 1, you're going to add 1 electron. So it's going to be 1s2, 2s2, 2p. Instead of 5, you're going to have 2p6. You're adding an electron there. All right, so I have my 1s2. Now for 2p, is what's going to happen is I may have now 2, 4, 10 electrons, but I'm still going to have 9 protons. Over here, remember, it's even. It was 9 protons and 9 electrons. Over here, it's almost like a tug of war. The 10s are going to win. They want to spread out. They don't want to be near each other. 1, 2, 3, 4, 5, 6, 7, 8. They want to be near they don't want to be near each other. They repel each other. So they're trying to get their own space. They're trying to move away from each other. So even though the protons are trying to pull them in, there's only 9 protons pulling in on 10 electrons. So they lose a little bit of their power there. But also, the electrons are trying to avoid each other. So we end up getting a much larger radius. So it's larger. It increases. So your anion is going to be larger than the atom it comes from. Now we've got, what, 2 more here? Yeah, 2 more. Ionization energy is your next one. It's the energy required to remove an electron. Okay, to take an electron away. And if you've ever played Old Maid, the point of Old Maid is you deal out all the cards. Let's say it's you and one other person. So somebody gets half the deck, somebody else gets half the deck. But it's not exactly half. There's enough that every single card is a match except 1. And if you're playing with a normal deck of cards, you take out one of the queens, because the other queen, the one that's left, her pair, is the old mate. They end up by themselves. If you have the ones that are just cartoon, you just have no mate. So it's an odd number of cards. Somebody has one more. Whoever is what you do is you pick a card from the other person's hand, and you try and make matches all the way through. You don't ask them for anything. It's not Go Fish. You pick one blindly from somebody else's hand, and you make pairs. Whoever's left at the end with one card left, being the old maid, is the loser. So if you play this with a little kid, they have half a deck of cards in their hands, right? 26, 27 cards. They've got them in their hands, and you have to pick one from them. It's very, very easy. Okay, the little kid can't really hold on to the cards that well. It's hard for them to do that, to control all those 26 cards. Now, as you get towards the end, especially if the kid's the old maid, they tend to hold them a lot tighter, especially the ones they don't want you to pick. The old maid always seems easy to take away. But they hold them a lot tighter because they can. They have more control. It's the same here for ionization energy. The protons, when they don't have a whole lot of electrons, they can control it easier. So the smaller your radius is, the larger the energy is going to be to take an electron away, because the protons can control a smaller atom better. Now, the bigger the radius is, the easier it's going to be to take an electron away. So you're going to have much, much less energy to remove an electron, because it's harder for those protons to hold in those electrons that are way out in the outside ring. So remember, for radius, as you go down to family, it got bigger and bigger and bigger, because we're adding more and more rings. So the energy is going to decrease as we go down. It's going to be the opposite trend, because the bigger it gets, the less energy it's going to be to remove one of those electrons, because they're farther away from the protons. It's farther away from that nuclear force. Now, going across the period, remember, the radius got smaller, it decreased, so our ionization energy is going to increase as you go across, which makes sense, because it's going to take a lot more energy to remove an electron all the way at the end, like fluorine or chlorine. They want to gain an electron. They don't want to lose one. So as you go across, the energy is going to increase, because the atom itself is getting smaller. It's going to be easier for the protons to hold on to them. Now, our question right here says, can lithium lose more than one electron? Remember, lithium is 1s2, 2s1. It's the one we just used as our drawing. Obviously, since I drew it already, this electron can get lost very, very easily, right? Remember, it looked like this. And that one in the outside ring really, really, really wants to go away. So let's say that one goes away. Yes, that obviously can go away. I already did it once for you. So you're down to 1s2. The question is, can it lose another one? It's stable here. Okay, it's just like helium. It's happy. Yeah, it can. It has two. Yes, it is very possible. But you have to remember, we have 3 positives pulling in on 2 negatives. It's going to take a whole lot of energy to try and take that one away. Now, for ionization energy, noble gases don't really come into it, because they're not going to gain or lose an electron. So they'll always have the highest electron or ionization energy. But this one, once it's already lost one, it's going to take a lot more energy to lose more. Okay, so you have to be careful of those ions, especially the cations. The last one is electronegativity, and that reflects an atom's ability to attract electrons to itself. Let's use blue. To attract. In a bond. Okay? So it reflects the atom's ability to bond. That's probably what that one blank is supposed to be. But I want you to know that it's actually the ability to attract electrons to itself, which forms that bond. So the smaller it is, the easier it's going to be to attract electrons from somebody else to it, because it's going to be close to the outside. Now, the bigger it is, those protons aren't going to be able to attract its own electrons, let alone somebody else's. So it's going to have the same trend as ionization energy. So the bigger it is, the less energy it's going to need. So as you go down, it's going to decrease. And as you go across, it's going to increase, because they're going to get smaller. And the smaller it is, the easier it's going to be for the protons to pull in. So the most electronegative, if you're looking at the periodic table, is fluorine. And the least is francium. Okay, because fluorine is our smallest radius. Remember, we're not really taking into account our noble gases, because they don't react with anything. and francium is our largest. We'll put atomic radius, sorry. So they're going to be the least electronegative because they're so large, the proton has to kind of pull through its own electrons before it can pull anybody else's. Whereas fluorine is your smallest atomic radius, so it's very easy to attract to something else. Now, the variable to that is, of course, hydrogen. It's much smaller because one has one. It only has one ring. So obviously, hydrogen bonds to a lot of things, which is how we get acids and all that good stuff. So hydrogen, I guess, technically is the most electronegative. But since we're doing trends, I want you to be able to look at a periodic table and tell this. I want to show you the two corners of the periodic table. Let's take a look at this. We've got fluorine up here, francium down here. So this is big, this is small. That way, if you're comparing two, let's say you're doing La and yttrium, you could tell that lanthanum is going to be bigger just because it's closer to your biggest. Okay, so that might help. There's also this periodic table, which I'm going to put on Moodle. You don't get this on the test, but some people need it visually. You know, it kind of compares atomic radius, ionization, or electronegativity, and how it looks on the periodic table as you go from left to right and up to down. And you'll notice these two trends, like I said, are the same. This one, atomic radius, is the opposite. So in all honesty, all I know is atomic radius, because that's what makes the most sense in my head. I know atomic radius, as you go down, it increases. As you go across, it decreases. And then the other two are the opposite.